When you come into this is mineralogy part. There are various types of mineralogical compositions, silicate structures, and what type of minerals which it's going to be formed in crystal system. And as per the mineral formations, there are various types of structures we will study. First of all, what it is a mineral? What it is a mineralogy? Yeah, mineralogy, we know that it's a study of scientific study of minerals. It's consisting of different types of chemical compositions, and it is a mineralogy. It's a special branch of geology. And not only that one, and it's providing to understand the physics and chemistry and genesis of different minerals. Those minerals, how they are going to be formed, it's depend on the chemical compositions. Yeah, definitely we can say a mineral, it can be defined as a homogeneous solid body, and it's occurring naturally. It is inorganically formed. It's inorganically formed, and it has a definitely chemical composition. It has definitely chemical composition. So the origin of a mineralogy, it's olden days. Actually, it was in 4,000 years ago. There were some records. As per that, we say, yes, the minerals also playing the very important role in human life and in economy also. The first book was written by the Aristotle and then Theophrastus during the 1st century. And after that, in the 1st century, Pliny was described the several minerals, including some gemstones. We know that mineralogy, it's emergence, it's a science through the public publications. Georgius Agricola, it was published one publication in 1556. He was a German physician and is known as a father of a modern mineralogy. After that, in 1669, Nicholas Steno, he was contributed the growth of a crystallography. And slowly, in 1770s, A.G. Werner, he was succeeded to explanation of minerals and external appearance of minerals in 1828. And after that, different types of minerals, they were invented by the different scientists like Pedro, Carlo, and Schoenflies. The advanced theories for internal symmetry of crystals, and it's a form as a basis for X-ray crystallography. In 1912, the Max Owen, Liu of University of Munich, he was demonstrated the X-ray diffraction by the crystal and explained how the diffraction patterns can be interpreted to give actual position of the atoms in the crystal. Thus, it was proved the first time that there is no yeah, there is a no alternative source. In orderly that the arrangement of atoms in a crystals, how they were arranged. And after that, the Braggs in 1914, British scientists, he published their work on a crystal structure and determinations. In addition, the improvements of were made in a technique and electron microbe provided it's a very powerful tool for the study of chemistry and other minerals. Yeah, minerals are classified into the two groups. It's classified into the two groups. One, it is one, it's a rock forming, and second one, it is economic. In a rock forming, minerals are very important. It's a constituents of a rock, such as orthoclase, augite, biotite, hornblende, etc. and etc. Suppose economic minerals are very important and it's very useful for a society. We know that hematite, but example for hematite, bauxite, galena, etc. and etc. These minerals can and metals can be get extracted from the economic sources for economic sources. And not only that one, the minerals can be classified as a primary based on the source. It's a primary and a secondary. The primary minerals, how they were formed. These primary minerals were formed as a product of the magmatic consolidation. That means when the magma it is going to be crystallized, it has a different types of the chemical compositions. As per a temperature, it's required when it is going to be crystallized at the time, the different or various types of minerals which are going to be formed. For this purpose, the primary source, it is a magma here. Or else when you go into the second case, that's a second class. The second class, it is a secondary minerals which are formed due to the operation certain process on early formed magmatic bodies. That's maybe the quartz. It is actually we know that it's a primary origin, and the malachite it is a secondary origin. From petrological angle, minerals can be classified. It can be classified into a essential and B, it is an accessory. What are the essential and what are the accessory? In essential minerals, these minerals are dominate and decided the name of the rock. Essential means it's occupying the major place when it's a rock, it's going to be formed. It's going to be as a mineral. It's playing a very important role. And based on this, we will give the name to the rock. The second case. In a second case, accessory minerals are least proportion and the significant the naming of a rock. And when you come into the accessory minerals are the least proportion which are presented very less proportion in a rock. It's presenting very less proportion in a rock. So when we are giving the naming to this rock, we will not consider a very major portion. For example, for potassium feldspar, it is an essential mineral in, and biotite, it is an accessory mineral in a granite. Yes, we know that the potassium feldspar, the quartz, it's very essential in a granite. Very essential in a granite. That's a potassium feldspar means maybe it is a pink granite and it's playing a very important role. It's a major role. But at the same time, we may identify the granite in a granite that's maybe it's a biotite or a mica. Sometimes we can identify. So here it is recognized as a accessory. The potash feldspar, it is recognized as a essential because of its occupying the major portion in a granitic rock. However, the most important scientific classification minerals, it is based on the chemical composition only. The maximum, whatever we are going to give the classification or a name to the particular mineral or a particular mineral based, we will give the name to them, and those it's depend on their chemical composition. As per J.D. Dana, he was a great American mineralogist, and he was made into the some subdivisions. What are those? If you see in a native elements like a gold, copper, manganese, sulfide like galena pyrite, sulfur salts, haloid like rock salt, oxide like quartz, oxygen salt like feldspars, pyroxene, amphiboles, calcite, and etc. and etc. And organic salts and organic compounds like hydrocarbon, carbonaceous materials like. These are 8 categories are very important in a mineralogical point of view. And again, there are various minerals have been grouped into the certain families. It is based on their structural affinities and similarities. Sometimes we may identify these type of group of minerals. Suppose example for if you see the silica group, and second one it is a feldspar group, third one is a feldspatite group, fourth one is a geolite group, fifth one pyroxene group, sixth one amphibole group, seventh one garnet group, eighth one epidote group, ninth one is a mica group. These minerals, what we mentioned, these group of minerals is deal in detail independently with reference to their physical and optical properties. Based on the chemical compositions and mode of availability or occurrence, depend on their uses also. The additional groups which will be also added. There are many properties of minerals. Mostly it is depend on their chemical composition only. Definitely. Just example for if you can say the pink granite. The pink granite, how it will become the pink color to the granite. We know that the pink granite, the composition of a pink granite, it is a pink potassium feldspars. Potassium feldspars. So here the potassium feldspars which are indicating as a pinkish in color, so that automatically the final composition of a granitic rock it is indicating in the pink color. So that here depend on the chemical composition, must and should the chemical composition is playing the very important role whether the mineralogical formation is going to be in a sequential manner. And one more thing it is, if you wanted to study about the geochemistry of earth crust, earth crust and the chemical structures, definitely we need some geophysical investigations also, which are useful for to reveal the discussing about the earth parts like crust, mantle, core. We know that the crust, it is a very uppermost. It's uppermost shell of the earth, and the thickness it has around it is 30 to 36 kilometers of a thickness. Under that, continents 10 to 13 kilometers. Oceans, it's occupying the place. And also, the crust, it's only it's a significant part of the earth, and it is in a thin layer. or we are calling that is like a skin of a apple. When you come into the mineralogical point of view, the earth crust it's depend on the different chemical compositions it's containing, and the determination of elements in the crust. It is easy to it is easy. It's not easy to explain, but it is difficult. According to the Michael Clark and Washington in 1924, the upper 10 miles, its consistence of igneous rocks, or maybe it is either maybe it is a metamorphic equivalence. An extent above 95 percentage, it's followed by the 4 percentage of a shale, 0.7 percentage of a sandstone, 0.2 percentage of limestone. The composition of a crust, therefore, it would be more or less the average composition of a igneous rocks should be see in a crust. Yeah, we know that there are major 3 categories of elements. One, it is a major element. Second one, it is a minor element. Third one, it is a trace element. If you see, it is obviously there are 8 elements were presented as a major, or we recognized as a major elements. Those are useful for the making of a Earth's crust. It's nearly playing the very important role, and major portion it is archbite. Those elements are like oxygen, silica, aluminum, ferrous, calcium, sodium, potassium, and magnesium. Almost it is a 99% which are present in a Earth's crust. And second stage, it is second stage it is titanium, hydroxyrum, phosphorus, and manganese range of amounts. Maybe those are present into the 0.1 percentage to up to 1 percentage. And these are these type of elements we are calling that is the minor elements. And then the remaining percentage, it's maybe 0.5 percentage, that's less than 0.5 percentage. It's containing in Earth's crust. These are all important for economically. And it's called as a trace elements. The Earth's crust, which is made up of over 80 elements, it contains nearly 2,000 minerals, out of which many are very rare occurrences. The average compositions here mentioned, but actually we know that the ppm level of oxygen, it's a 4,66,000 of ppm, and 2,77,000 of 200 ppm. Approximately, it is a 27% of a silica, 46% of oxygen, 8% of alumina, and remaining all those occupied by just 5% and the 3.6%. It's respectively iron, calcium, so sodium. These all will be there. Yeah. When you come into the weight percentage of these major elements, just now I told you that is oxygen, it is a 46.6%, silica 27.7%, alumina 8.13%, iron 5.00, magnesium 2.09, calcium 3.63, sodium 2.83, potassium 20.59%. Weight percentage will be available on Earth crust. Yeah, As per this, we need to study about some structures. The silica, how it is going to be assessed. If you take any mineralogical composition, if you see any mineral structure, definitely the hidden, definitely it has a silica structure. Let us see the silicate structures. The crust contains 95% of silica minerals. From this 60%, majorly it is occupied by the potash feldspars or feldspars, and 12% it is occupied by the quartz. Quartz and the great group of silicates, which are the most important rock forming minerals. The silicates were formerly considered as salts of silicic acids, but now in their classification, it's made on the basis of crystal structure of compounds. In a silicate structures, the atoms of silica, it's found, we have to found that is in 4 coordinations with a one oxygen. With oxygens. The silica atom, it is situated in a center. Look like it's a tetrahedron. The other corners, it is occupied by the oxygens. So that here, silica structures in silica structure must ensure the silica, it should be in center, and the remaining oxygens, whatever oxygens, it will be presented in that structure, and these will be occupied by the tetrahedron shape. So that here in the tetrahedron means it's a 4. So here finally we can say that is a SiO4. SiO4, it's a tetrahedra, silica oxygen tetrahedra. Maybe the distance, it's a distance, the centers of 2 adjacent oxygen, it's a twice. It is in a radius of oxygen, and the different silicate, the different silicate type arise from different ways, in which in particularly only silica and oxygen tetrahedra. Yeah, sometimes we may identify the independent tetra groups also. In independent tetra groups, what we discussed, the silicate structure, where it is the silica, it is associated with the 4 bonds of oxygen atoms. And similarly, the silica and oxygen tetrahedra present as a separate unit, and that's the composition, it would be SiO4. SiO4, that's the best example for the forestite, Mg2SiO4, and the group of a silica, it is known as nesosilicates. Nesosilicates. So here again, what it is a nesosilicate? The independent tetra groups, what we are saying, in a silicon and oxygen, in tetrahedra, it's present as separate units, and the composition, it has a SiO4. If you see, it is in forestite, Mg2SiO4, and this group, it is known as a silica group, or a silicate group, or a nesosilicate. Neso means it's a meaning of island. It's a meaning of island. Double tetra structures. In a double tetra structures, sorry. In a double tetra structures, the silica oxygen tetrahedra, it may occurs in a pair. In pair, which pair are linked by the sharing of one oxygen between the 2 center structure, and and the composition it would be the Si2O7. Si2O7. In a center part, definitely it has a two centers. That's a Si2 composition, Si2, and the remaining one oxygen it is in a mid. It should be in a mid, and the other side three oxygen atoms, three oxygen atoms will be joined. So that here in a double tetrahedral structure, in double tetrahedral section, the oxygen it should be in middle, and the other side two silica atoms will be bonding with this one, and the remaining three oxygen atoms also it will be having a bonding with the silica atoms. So here it's finally it is showing as a Si2O7. And the best example for this one, hemimorphite. In a hemimorphite, that's a ZnSiO2, Zn4SiO2O7, OH taken twice, and H2O. This type of silicate, it's known as a sorosilicate. It's sorosilicate. Yeah, next one, a ring structure. In a ring structures, two of the oxygens which are arranged with the adjacent tetrahedra, and linkage takes place in each SiO2 tetrahedra, and it's shades in which a way so as to form rings, and the resulting composition is Si3O9. Si3O9, or if it is a double, Si6, and automatically the oxygen ratio it is also going to be double, Si6O18. The best example for this one, it is a bentonite, bentonite, bentoate. The chemical composition, it is the BATISI3O8. And this bentoate with three tetrahedra, and beryl B3SB3AL2Si6O18. It's related with the sixth tetrahedra. These type of silicates are, it's known as a cyclosilicate. The cyclo means it's a ring type structure. It has a ring type structure. Yeah, another one, it is a chain structure. In a chain structure, there are two chain structures. One it is a single chain, second one it is a double chain. In single chain structures it's are found in a pyroxenes, and double structures we may find in amphiboles. The tetrahedra, it's a linking together to produce the chains of a indefinite extent. In single chains, if you see in a single chains, the ratio between the Si is to 0, it is indicating as a 1:3. Or else if you see the same in a double chains, that should be as a 4:11. So these type of single chains, Si is to O, it is maybe 1:3. it's a 1:3. And the double chains, if you see, that is a 4:11. In a double chain structure, two single chains are present. Side by side, it will be come. And there is a interval. There is a regular interval between the oxygen atoms. So that here, this type of group of silicate, it is known as a inosilicate. Ino, it's a meaning of this one. In Greek, we are calling that is as a chain. In ring structures, it is called as a cyclo. Cyclo means ring. In double tetrahedral structure, that it is called as a soro silicate. So soro silicate means here, soro means group. Yeah, one more, that is a final one. It's a sheet structure. In a sheet structure, it's formed when SiO4 tetrahedra are linked by 3 of their corners with 3 oxygens of each tetrahedron. In this case, Si is to O, that is indicating as a 2:5. It is indicating as a 2:5 ratio. And it is found in all flanky minerals, such as mica and chlorite. The sheets from hexagonal network, and it's responsible for a pseudo-hexagonal form. And the cleavage, it's being parallel to plane for sheet in a micas. This division, it is known as a phyllosilicates. Phyllon means here leaf type, or it is a sheet type structure. So that we see here completely, there are 5 types of silicate structures based on the availability of the silica formations. One, it is nesosilicate. Second one, it is the sorosilicate. Third one, it is the cyclosilicates. Fourth one is inosilicates. Fifth one, it is a sheet structures. It's called as a phyllosilicates. There is a framework for structures or 3-dimensional networks. In such structures, each silica and oxygen in tetrahedron shells are its corners with the ratio that is 1:2. The feldspars and quartz, it's having the same structure. And the final, it is known as a tectosilicate structure. Tectosilicates. It is called as a tectosilicates. Yeah, finally, we know that the mineral, what it is a mineral. Yeah, it's a mineral. It is a homogeneous solid body, and it occurs very naturally, and should be, it is available in an inorganic form. And definitely it has a chemical composition. Yeah, some physical properties of minerals. Let us see. That is physical properties of there are. Suppose if you wanted to observe for each mineral, it has a own physical properties. We see Some of those, it's very characteristics and differentiate from the mineral if we each other. These properties can be determined either by the inspection of a mineral sample tests, and it's a determinated in his hand specimens, and they are very important to identification of a minerals. The properties, whatever we have, and is greatly practical significant as they can be readily redomined for each identification of a minerals. What are the common properties of minerals? The common properties are color, streak, luster, hardness. These are the common properties of a minerals. Yeah, just we will discuss the basic things. Cleavage, parting, fracture, tenacity, form, structure, and specific gravity. These are the must-and should we have to create when we are observing the any mineral. The mineral, it's a exhibits. First, we see the color. The minerals exhibit the great variety of colorals, and the color of a mineral, it's usually not dependable or distinguished characters, and it's produced either due to the reflection, it's due to the reflection, or maybe sometimes it's a transmission of a light. The transmission of a light, particularly we have to selective absorption within it will fall on the surface of a body of a mineral, so that it is automatically it will be getting the reflection. Here the main cause of colors, how the color it is generated, it's depend on the mineralogical compositions. The minerals which are having a different types of chemical compositions, as per that the colors which is also exhibiting to outside. It's a very fundamental property. It's very basic property, and it is directly related with the chemical composition of whatever mineral we are observing. In some cases, it is related to the chemical composition, but sometimes it is depend on the crystal structure also. So that in other cases, it is due to impurities, or sometimes maybe it is not have a clarity of a picture, and minerals which exhibits constant and characteristics of a color, it's known as a idiochromatic. It is known as a idiochromatic. Then what is happening? It's producing or exhibiting the constantly, it's exhibiting the color. The property it is known as a idiochromatic. These type of minerals which are shown in a different color or in a variable in color, the term it is known as a allochromatic. It is known as a allochromatic. And there are some metallic minerals generally which are exhibiting exhibiting the consistency in a colors and than the non-metallic minerals. Due to the interreferences, the light, either it is on the surface or there, sometimes if it is an interior of a mineral series of a colors, it's produced in the turning about in a light. When it is a rotation of a color change, it's rapidly in a succession. Maybe that will be happening in diamond. Because of in diamond, it's a maximum, it's having a very close association of atoms between the carbon. So that when we are rotating this diamond under the light, it is exhibiting the different colors. It is exhibiting the different colors because of it's absorbing the light and immediately it is emitted. Because of the closeness, it's very high between the atoms. So that is the reason. And some of the minerals which are showing the rainbow color, either it's internally or on the surface. The internal phenomena, it can be caused by light diffracted or reflected. There are two from the fractions. It's a cleavage planes, and another one it is a set of cleavages. Some of the specimens of labradorite show colors ranging from blue color to the green and green or a yellow. Because of when the angle, it is an instance of a light changes. When the light it is a fall on the mineral, if it is an instant on a mineral, then immediately it is getting the reflecting based on that angle. At a certain angle, if you can rotate, that is going to be changes. The light, it is going to be changes from blue color to the green or blue color to the yellow. That will be happening depend on the composition of a chemical elements. The surface phenomena, it is due to it is a interference of a light whenever it is reflecting from the surface, and generally the metallic minerals such as a hematite, it shows this property. In some other minerals, the surface rather dull and its a color, it is a different from the true color. The best example for this one, Bohr Knight. Bohr Knight in the true color, it's shown by the freshly broken surface. Or else if you see the bronze color, but it is quickly turned into the purple violet due to the oxidation and exposure. Yes, definitely this is. Suppose if you can see the color of a fluorite mineral, example for fluorite mineral or scheelite. If you see the fluorite at outside without any applying of a UV light and other, just at the time, just we can able to see these color. It is in normal in white color. Again, the same if you can put under the ultraviolet rays or usable UV light, then the original color it will be appear down. Slowly once the color, if it is a fall on the same fluorite mineral, it is absorbed, immediately reflected in some rock. But particularly when you come into the UV light, the fluorite is absorbing the UV light and slowly it is appearing as a blue color or a purple color. What's happening there? It is absorbing. It's absorbing the color whatever we are observing, and slowly, yeah. That means here, because of what is happening inside of this crystal structure and inside of this mineralogical composition, mineralogical composition of rock or a mineral, the color it is absorbing by the different chemical elements whatever presented inside, and then it's emitting the light to outside. So according to that, the color it's appearing. According to that, the color it is appearing. Yeah. The same example, whatever Bohr Knight, if you can see the Bohr Knight, it's a freshly broken surface. Or if you see the bronze color, that is in a bronze color. The Bohr Knight, if you can break into the pieces on a surface, it is appeared into the bronze color. After some time, so what happened? And slowly it is turned into the purple violet. Because of that is the oxidation. Due to this is the oxidation process. And it is appearing, or it is converting, or into turn into the purple violet. The same principle you can apply into the just oxidation process in an apple cutting method. You see, when once if you can cut the apple, just you can put it outside for a few minutes, and the original color it is going to be lost, and the gray or a blackish color it is going to we can able to see, because of what is happening. Once if you cut that, the in the atmosphere the oxygen it is going to be reacting with the what we have cut the pieces, it's reacting with them, and the oxygens which are absorbed by the material, and finally the color it is going to be changes very quickly. So the same principle it is also here, it is going to be applied. That is in Bohr Knight. What's happened in Bohr Knight? Just you can broken the surface of a Bohr Knight, and immediately it is absorb the oxygen, and then due to or in the process of oxidation, and the Bohr Knight slowly the color it is going to be converting into the purple and violet color. Yeah, they these are all the various processes which are participated in different different colors, different minerals which are showing the different colors because of due to the internal structure of chemical elements in a rock composition. And I'm stopping here, and tomorrow we will see the streak, luster, hardness, and cleavage, the other properties of a cleavage, parting, fracture, and tenacity. Forms and structure also, that's also very important. and pseudomorphism, polymorphism, isomorphism, specific gravity of minerals, how we can find out the specific gravity, and Joly's spring balance. In Joly's spring balance, we can use here Archimedes principle, how it will be working, the minerals, how we can weigh, and one more, it is pinkometer, it will also there. It is useful to find out the specific gravity of small pieces of minerals and some other heavy liquids, and rare properties also we'll see tomorrow in class. Rare properties means in phosphorence and fluorescences. Once the light, if it is the fall on a mineral, how it will be behaving, and feasibility, magnetism, electricity. We'll see in tomorrow class.